Imagine a tiny spacecraft hundreds of millions of kilometers away. Yet NASA precisely guides it to photograph a target. Every command from Earth takes tens of minutes, sometimes hours, to reach the vessel. So, how do they manage this? The answer isn't real-time remote control, but a blend of precise physics and onboard artificial intelligence. NASA first needs to launch the spacecraft with extreme accuracy, using planetary gravity to slingshot and conserve fuel. Once it has traveled an immense distance, the spacecraft must find its own way. It cannot wait for commands from Earth. The speed of light itself creates a huge challenge. Every course correction requires a long, anxious waiting period for confirmation. This deep space probe is essentially an autonomous robot, programmed to make decisions and troubleshoot without human intervention, to determine its exact position in the vastness of space. The craft uses special cameras to photograph familiar star patterns. This star tracker navigation system is incredibly precise, allowing the craft to determine its location within just a few meters, as it approaches the asteroid. A key technology activates optical navigation. The probe's eyes. Optical navigation allows the craft to recognize the asteroid, calculate its own trajectory relative to it, and autonomously correct its path. It's like the craft has eyes and a brain, constantly comparing the real-time image with the pre-programmed map. Every time the craft takes a picture, data is sent back. Engineers review it and send small, vital fine-tunings. This process is not continuous. For most of the time, the craft must operate independently based on the large plan uploaded earlier. The craft uses small maneuvering thrusters to perform subtle, delicate nudges, ensuring it doesn't drift off target, despite the enormous distance. NASA requires a massive, powerful communication system to maintain its link. This is the Deep Space Network, DSN, 3 colossal antenna stations strategically placed across the Earth. The DSN ensures that, regardless of Earth's rotation, there's always an antenna that can see the distant probe in space before the craft executes a flyby or landing. Engineers must run thousands of computer simulations. The programming must account for everything, from the asteroid's minuscule gravity to the photon pressure from the sun. The hardest part is the asteroid's extremely low gravity, making it like trying to stick to a floating particle of dust if any issues arise, like a software glitch or equipment failure. The craft is also programmed to save itself. This fault protection system is a rigorous set of rules, allowing it to automatically switch to backup and redundant systems. The entire procedure is a dance of precision, where the craft must balance obedience to command with full autonomy. The scientific instruments on the craft are automatically activated when it reaches a certain proximity to the target. In mission control, personnel primarily monitor. They rely heavily on the craft's self-operating capability and preparation. When the craft successfully collects a sample or data, it compresses it and prepares for the transmission back to Earth. The data is complexly encoded to travel through millions of kilometers of cosmic noise and interference. The data transmission rate back to Earth is incredibly slow, sometimes comparable to an old-fashioned dial-up modem. Controlling the robotic arms to collect a sample requires even higher precision than navigating the craft itself. The entire process, from taking a picture to sending a corrective command, must account for the communication time delay. A slight timing error could cause the spacecraft to miss its target by tens of thousands of kilometers. The craft must constantly keep its solar arrays pointed towards the sun to ensure power for all critical systems. Maintaining a stable orbit is a continuous challenge, requiring small, frequent firings of the maneuvering thrusters. Every deep space probe has redundant computer systems to ensure there is no single point of failure in the mission. As the craft approaches, it takes multiple pictures from various angles to create a precise 3D model of the asteroid. This detail helps scientists pinpoint the safest and most scientifically valuable spot for sample collection. The thrusters must generate extremely small forces, just enough to apply a delicate change in velocity, delta V, occasionally. The sun passes between Earth and the craft, causing a complete communication blackout for several days. It is like trying to accurately throw a dart at a tiny bullseye hundreds of meters away from you. Thermal sensors are also employed to map temperature distributions, helping to better understand the asteroid's surface properties. Upon mission completion, the craft sends back final images, confirming the success of a true engineering marvel. It has autonomously placed itself into a safe orbit, awaiting further commands or entering a hibernation state. This precision is not luck, it is the culmination of decades of research in physics, automation, and deep space communication. NASA's asteroid exploration program proves that nothing is too far away for human technology and ingenuity.
If you find this video useful and want to explore more interesting things with me, don't forget to like and subscribe to the channel. Now, goodbye and see you again in the next videos.